Hello everyone. Today we will have introduction to artificial neural networks. Artificial neural networks have been popular recently. In fact, the so-called deep learning started with artificial neural networks, and now there are many variants available like CNN, etc. But there is a similar technique available in traditional statistics. So that is known as projection pursuit regression. Okay. So projection pursuit regression is similar to the modern concept of artificial neural network. How they are similar and the basic structure of artificial neural network we will see today. As the name suggests, neural network tries to mimic functioning of human brain. Human brain has neurons, and one neuron fires another neuron, and that's by transmitting a signal, and that's how body learns things or body performs certain actions. Okay, so here also a network of neurons is constructed, and then the signal or the data basically travels through that network. Okay, and what is the meaning of the word projection? You might be knowing already. Reducing dimension of the data is equivalent to projection. For example, when we see a shadow, it is basically a projection of 3D object to a 2D plane. Okay, so if I have some three vector in 2D like this, so this is a vector, so its projection on x-axis would be this point, its projection on y-axis will be this point, and so on. Okay, so projection pursuit regression is basically conversion of multivariate data to some low dimensional projection. Okay, so how do we do that? So suppose we have p variables x1, x2, xp. Okay, so in normal regression what we do is our model is y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta p xp plus epsilon. This is our usual regression model, that is linear regression model. One of the disadvantages of linear regression model is it captures only linear relationships. So if the relationships are not linear, then it doesn't do very well. That factor is taken care of in projection pursuit regression. How is it achieved? So what we do is we construct a new m-dimensional vector, and that is done via taking the projections. So we will have x vector as x1, x2, xp. Okay, and then we will have now new m p-dimensional vectors. So v1 is p cross 1 vector, v2 is also p cross 1 vector, and so on. Vm is also p cross 1 vector. Using these, we will construct v1 prime x, v2 prime x, vm prime x as a new vector. You can see the dimensions. v1 prime x is 1 cross 1, v2 prime x is 1 cross 1, vm prime x is also 1 cross 1. So finally, this is m dimensional vector. Okay, this is m cross 1 vector. In fact, our PCA is one such example. Okay, so v1 is an eigenvector. v1 is first eigenvector, v2 is second eigenvector, and vm is mth eigenvector. Okay, so PCA is one classic example of such projection. So we first convert this, and then now we define y as sum over I going from 1 to m fi vi prime x plus epsilon. Okay, where this fi can be any function. It could be a linear function, it could be a non-linear function. As a result, what happens is by vi prime x, I am getting first a combination of multiple variables. Okay, and by applying fi to that combination, I am now considering more flexible class of functions than the linear regression. Okay, let us take a small example. Suppose v1 is say 1 minus 1 and v2 is 1 0. Okay, so suppose I have only two variables x1 x2, hence v1 and v2 are also 2 cross 1, so they are primes of this. Then what will be v1 prime x? v1 prime x will be x1 minus x2. v2 prime x will be simply x1. Okay, and suppose we take f1 x as e raised to x and f2 x as suppose sine of 1 by x. Then how will my y look like? My y is supposed to be this, right? So my y will be, y is a scalar, I'm sorry, y is a scalar. So y will be f1 of v1 prime x plus f2 of v2 prime x plus epsilon. So y f1 of v1 prime x will be e raised to x1 minus x2 plus v2 prime x is just x1. So this will be sine of 1 by x1 plus epsilon. So you can see how much flexibility this model is giving us. So I have combinations of xi's and I have nonlinear functions of x. Okay, so everything in one. So this is projection pursuit regression, and artificial neural network is similar to this. We can have even more flexibility. We can say that I won't assume any fixed form for FIs, and that FIs can be completely data driven, like in the case of non-parametric regression. Then this becomes a semi-parametric model. Okay, so now let us see a structure of neural network. So let me start with a very simple network which has what is known as single hidden layer. Okay, what do I mean by that? We will explain. So I have p variables as input. So I will first construct p nodes x1, x2, xp. These are p input nodes, and we know that sometimes we have to add a constant like an intercept term in regression. So I will have one more node here which I denote by 1 to add constant. Okay, then so this is known as input layer. So input layer will have 1 x1 x2 up to xp. Okay, then a hidden layer, what will a hidden layer have? A hidden layer will have new variables. Okay, so 1 z1 z2 zm, these are m newly constructed variables, and it will also have some constant. And then I will have an output layer which will give me y. Okay, a network is basically connection of this. So every node in the input layer is connected to every node in the hidden layer. Okay, can you see this? Every node in the input layer is connected to every node in the hidden layer. Similarly, every node in the hidden layer will contribute to the output layer. Okay, so this is how the network is constructed, and in hidden layer also we have constants. Okay, now connected means what? Connected means we will have some weights and some functions will be applied. So the weight of this constant, in this constant we will denote by alpha naught naught. Okay, then weight of this constant in z1 I will denote by alpha naught 1. Then to z2 it will be alpha naught 2, and so on. Okay, so I will have how many alphas? So I will have alpha naught naught, alpha naught 1 up to alpha naught m. Okay, so this is for constant to constant, constant to z1, constant to zm. Okay, then I will have alpha 1 naught, alpha 1 1, alpha 1 m. Then I will have similarly alpha p naught, alpha p1 up to alpha pm. So how many total? So here I have m plus 1 weights, again I have m plus 1 weights, m plus 1 weights. So total we have p plus 1 into m plus 1 weights. Okay, these are like parameters of this neural network. Okay, and how are ZIs constructed using these? So any particular Zi we will construct as sigma of alpha naught I plus alpha 1I x1 plus alpha 2I x2 plus alpha pi xp. Okay, this becomes Zi. So I'll have z1, z2, zm like this. And from these Zi, we construct a new quantity called Tk. How is Tk constructed? Tk is beta naught k plus beta 1k z1 plus beta 2k z2 plus beta mk. Okay, beta mk zm. So how many TKs I will have? That also is our choice. And so we will see in a minute how many TKs we have in each setup, classification and regression setup. So K can go from 1 to up to R. In ZIs, I goes from 1 to up to M because there are M ZIs. Then there are R TKs, and then we finally define Fk of the vector x as some function applied to this t vector. Okay, now what is this activation function that we have to see, and what is this gk that also we have to see. So in a regression setup, generally we define only one t. Okay, in a regression setup we will have only one quantity t, which will be a combination of all these zi's. So betas will basically be weights for these. Okay, so betas will be weights for these. So this will be weight for this quantity will be beta naught 1, beta 1 1, beta 2 1, and so on, beta m1. Okay, so betas will be this weight, and in the regression setup I will have only one t, and this gk is taken as simply identity function. Okay, gk is taken as identity function. But in a classification setup we could have number of TKs as how many levels we have. Okay, whatever number of levels we have, that could be number of TKs. Okay, and in the activation function is like basically applying multiple types of non-linear setups. So one common activation function is known as sigmoidal activation function. It is defined as sigma of gamma as 1 plus e raised to minus gamma, or slight variation of it is sigma of s gamma is 1 upon 1 plus e raised to minus s gamma. So this is known as sigmoidal activation function. You can plot a graph of this and then you will realize why the name is sigmoidal activation function. There are other activation functions like linear. So you have something like this, or there is something called as RELU. Okay, so you have something like this. Okay, so flat up to certain point, and then this rectified linear, and so on. Okay, and as I said, for regression gk is taken as identity function, but for classification setup we need some sort of probability, okay, of each class. Hence for classification setup gk is taken as softmax function. We have seen softmax function in the case of logistic regression, multinomial logistic regression, right? So it will become g of g will be e raised to tk sum over e raised to tk, k going from 1 to r. Okay, so as I said, you have some combination of input quantities into the hidden layer to get to hidden layer. Then from hidden layer we reach output layer. But this is a very simple network which consists of only single hidden layer. But we could add complications by adding multiple hidden layers, and then there could be some other functions for transferring from this to this hidden layer. As a result, your model becomes more and more nonlinear, and hence more complicated patterns can be captured if there are large number of hidden layers. Okay. Of course, this also means that the structure will become more and more complex. You know that when we go from usual regression to principal component regression, one of the major disadvantages is that interpretability is completely lost. Okay, interpretability is gone because now your function is no longer a function of single variable, but it's a function of multiple variables. Same problem occurs in neural networks also. Your as you increase, in fact, even with a single hidden layer, your function is very complicated, and when you add too many layers, it becomes further and further complicated. Hence, this is called as black box model. You cannot have a concrete form. You don't know exactly how each variable is affecting your output. Okay. Hence, in the cases where this explanation is important, this model may not really be useful. But accuracy wise, it has more flexibility and hence it is more accurate. Nowadays, people have developed what is known as explainable AI techniques or interpretable ML techniques, where they try to perturb values of the input quantities by small margins and then try to see what is the effect of each individual variable in the final output. Okay, but that is done as a post hoc analysis. As it is, the model cannot tell us much about contribution of individual regressors in a given outcome. Okay, so let me stop here.